Everyone. So today we have two talks. For the first talk, we are very happy to have Jacopo Rubio, who was a postdoc in our group, and now he's at the Center for Mathematical Sciences and Applications at the Harvard University. And today he's going to talk to us about sections of smooth vibrations over P1.
Thank you very much for the introduction, and thank you for having me here. It's always a huge pleasure to come back to Taiwan. So today I'm going to talk about this joint work with ventures. It's currently in progress, but hopefully it's going to appear soon in the archive. I hope by the end of the year. But anyways, so let me start with some introduction and motivation. So just to set the stage, let me just recall what do I mean by a vibration. So a projective morphism of normal varieties. F from X to Y is a vibration, or also contraction, sometimes called. If the push forward of the structure shift upstairs becomes the structure shift downstairs. Okay. So in particular, this morphism always had connected fibers. Okay, so the starting point for our project was the following theorem of Pilock. I think it first appeared in 2022. Yeah, it's fairly recent. And the theorem is very simple. It says that if you have f from x to y, sorry, x to p1, smooth vibration, oh, sorry, I didn't say, but for the time being, for now we work over C, first of all, unless I explicitly say otherwise, and all varieties are smooth. So no worries about weird singularities. Okay. So if you have a smooth vibration x to p1, then F admits a section. Okay, so in general, having a section is quite a special property. Since the base is a curve in this case, this is equivalent to asking that the generic fiber has a rational point. And since you are on a non-algebraically closed field, this is a very non-trivial thing. Okay. Now, let me make a couple of remarks about this result. So, first of all, which is the thing that caught my attention, is that the only proof of this result is symplectic. So there is currently there is no algebraic proof of this result. It uses fairly advanced techniques of symplectic geometry. The second is sort of why should there be a section? So what is the heuristic behind this result? And the heuristic comes from Hodge theory. So you know that if you have a smooth morphism x to p1, then you can associate with a variation of Hodge structure. So if I look at the direct images of the constant structure shift, the constant shift C over X, right? So these form a local system over P1, and this local system is endowed with a Hodge filtration which satisfies a bunch of properties, and this is exactly what the notion of variation of Hodge structure can do. And there is a moduli space for Hodge structures D, let me call just D, and which is a period domain. And you have a period map file. And so it was shown by Griffiths that the period domain D is hyperbolic along period images. So in particular, what this is telling us is that this map here has to be constant. Because I mean you cannot map P1 into an hyperbolic variety in an unconstant way. So to summarize, whenever you have a smooth vibration over P1, a smooth family of varieties over P1, if you look at it through the lens of Hodge theory, this is essentially indistinguishable from a constant family. Okay, so Hodge theoretically, this is just a product. And so the expectation is that this Hodge theoretic triviality should be reflected in the products-like features of this family. And for example, the existence of section is such a feature.
Can I ask a question?
Yes.
So you say that the proof is symplectic. So then does the theorem also hold for complicated X, or you really need projective?
That's actually a very good point. So I don't know about the Taylor case, although I'm gonna say something in the end. But this is a work in progress, so don't let me not spoil too much. But the last point that I want to make is that this is false for complex varieties. So how do we see it? Well, take E, an elliptic curve. So this is just C mod lambda. So this is a lattice inside C. And then I can consider, let me call curly E. This is the sheaf of holomorphic function from E1 to E, crucially in the analytic topology. Okay, so this is a sheaf in the, I mean, of course, there is no such a holomorphic map on a Zariski open, but I'm considering it in the Zariski topology, in the analytic topology problem. And then it's not a hard computation, you can do it as an exercise, that if you compute H1 of P1 of this sheaf, this is non-zero. So in particular, what does this say? There exists non-trivial E-torsor over P1. Okay. And so in particular, this will give you, I mean, E-torsor is just locally is just a product E times P1, but then there are some twists. And in particular, so this is an example of a smooth morphism, a smooth family without section, because if it had, then it would not be, it would be a trivial. And so this is a special case of Hopf surfaces. I mean, this doesn't completely answer your question because these things are non-Kähler. But at least, I mean, we know that if you just look at complex varieties, this theorem completely falls. And last remark is that Pilot theorem okay when R has one singular pattern. But if you ask for two singular patterns, there is no. Any other question? Okay,
Varieties which this theorem doesn't apply. You said possible complex varieties.
no problem, I mean, non-algebraic.
Oh, non-algebraic.
Yeah, like compact, these are examples of compact complex, yeah. Yes,
Is it open so it's a conversion?
in this example, I mean, it's not all, I mean, it depends what you mean by obvious, but it's not that hard. Yeah, I mean, it's a smooth morphism with connected fibers.
So your last remark is equivalent to say that you can replace a P1 by A1 in your theorem.
Sorry?
Your last remark that it still holds when F has one singular fiber.
Yeah.
It's equivalent to saying that you can replace P1 by A1 your theorem, a fine line.
Well, I guess so, right? You can always compactify and solve the singularities over the.
Yeah.
Right.
Mm-hmm.
I suppose, yeah.
Yeah.
I mean, yeah, oh, yeah, I guess so, yeah. Okay, so, but our upshot, I mean, we have two questions that we wanted to answer. First is, we would like to understand this theorem algebraically. Because, I mean, I have a very limited understanding of symplectic geometry, so I would like to understand where these sections are coming from, using only algebrogeometric methods. And I mean, most importantly, at least for me, is I want to understand what happens instead when you move to characteristic P, because of course you cannot apply symplectic techniques to positive characteristic varieties. And so, I mean, if you can come up with even a partial proof that uses only algebraic geometry, then maybe you can say something in characteristic P. Okay, and so we proved two theorems that somewhat completely answer question 1 and partially question 2. So let me state them. So theorem 1 is the following. Suppose that you have f from x to c. Now this is a vibration. C is a curve. Okay, doesn't need to be p1, but it's a curve. And the vibration might not be smooth, but you know, since we are in characteristic 0, we can find a dense open such that when we take the pullback, we get a smooth vibration. And then I'm asking two things of this vibration. So first, I want that if I look at the variation of Hodge structure in degree 2 cohomology, this is a trivial. And I want that kx naught to be not f net, or f naught net. Then there is the section. Okay. So if you have so we have a vibration as a family of varieties, possibly with singular fibers, and I want a trivial variation of Hodge structure on the smooth locus, and then I want there to be some k negative curve in some smooth fiber. Okay. If you have this, then you have then you can show the dream. It's this direction. Yes, correct. Yeah.
Even the lyric direction is one.
Correct. Correct. Yes. The reason, I mean, you will see, I mean, I'm going to cover the proof, but the reason is that this is where so the relative neuron severity lives. And our second theorem is the following. Suppose that we have F now from X to P1, a vibration. Again, not necessarily smooth, but let me assume that the relative canonical distortion, direct intersection. Okay, and so and then it turns out that if you combine these two theorems and you assume the abundance conjecture, then you recover Euler's theorem. So let me recall what the abundance conjecture said. Was that X is a smooth projective. Abundance. A smooth projective modality such that the X is mesh. Then the X is semi-uniform. So corollary. So assume abundance. If okay, then you record. Follows from one. Okay, so today the plan that I want to what I want to tell you about is I want to give you an idea of the proofs of theorem 1, 2, and 3 in the first part of the talk. And in the second part, I want to tell you briefly what can we get in characteristic P using similar techniques. Okay. So proof ideas. So that I need to recall a little bit of machinery. So suppose now Y is a smooth projective parameter. And then we know we can associate these two free Z modules, N1Y and after 1Y. So these are co-dimension 1 cycles modulo numerical equivalence, which I'm going to identify with 3 powers. And these are free Z modules of finite rank. Rho of Y, got the rank. And inside the space of dimension 1 cycle with coefficients extended to R, there is this gadget called the Morricone of curves, MPY, any part Y. So this is the closed convex cone of effective one-siders. Okay, but you've seen some variational geometry, I guess, like you are very familiar with this gadget because it plays an important role in the minimal model program. And I mean, this is a closed convex cone, but it has an additional structure which is exactly is determined by Morris cone theorem, we call it. So first, that we have countably many KY negative functional curves, CI, such that the cone decomposes as follows. We have alpha cone, where K of Y is non-negative, and this one we can't really say much in general. But then the KY negative part is generated by the rays spanned by these rational curves. Okay, so yes, and there is this very suggestive picture. This is the hyperplane given by KY. And we have alpha of the cone where K is non-negative, and we can't really say much on this part. But in the other, we have that this guy is generated by these extremal rays. And I mean, there is another part of the theorem that we won't need, but these are countably many extremal rays, and it turns out that they can only accumulate near the hyperplane KY loops. And the second part of the theorem, so this is the cone part of the theorem. Then there is the contraction part of the theorem that says that for all extremal rays are equal spanned by some of one of these KY negative curves. There exists a contraction the GR from X. Oh, I call it Y, so to Z, which contracts such that minus KY is GR ample, and GR of any curve is a point if and only if the curve belongs to the ray that we selected. So this thing is telling you, okay, you select whatever ray you want, and then this theorem produces for you a map with connected fibers, which contracts only KY negative curves, and it only contracts those curves which live in the ray that you select. Okay, note that I'm not saying anything about the dimension of Z. It could be the same dimension, it could be lower dimensional, and I'm not saying anything about the singularities of Z. Of course, I mean, you can say something, but we won't really need this. But if you're familiar with the MMP, you know that there is a long story after. But we need just so this is for one variety, but we are working in a family, so we need a relative version of these notions. So, okay, now suppose that you have F from Y to C, now a vibration. So C is again a curve, but I'm not asking C or Y to be projective. So the morphism is projective, but C might be affine. Okay. And I also want it to be smooth. Okay, then I have the local system of flat families of one cycle modulo fiberwise numerical equivalent. So let me write it down. So I denote by curly Y sub curly N sub 1 of Y over C. So this is an eternal local system from PA to mod Z. And it just takes an étal open in C, and it sends to flat families of one cycles. So C over U inside Y base change to U over U. Modulo numerical equivalence again, but fiber one. And I mean, and similarly, you have an upper one version of this, which is defined analogously, and it turns out that these are local systems. Okay. And here, and if I look at this local system, I can extend the coefficients and take them the coefficients in R. And inside here, I can consider flat families of one cycles with non-negative coefficients. Okay. So, and this gives me a sheaf of cones, which are denoted by curly and curly E Y over C, which is the relative version of our model. These are flat families. Of effective one cycles with real coefficients. Again, modulo fiber-wise effective. So this is a sheaf of codes essentially inside this local system. Okay, now a small remark. It's useful to stop a moment and think about how does this guy behave with respect to restriction to a fiber. So in general, what you have is that if I take n upper one y over c, and then I take the fiber over a point in the curve, this thing will be equal to an upper one of the fiber for only very general C inside C. Okay, so in general, forming this local system does not commute with restriction to a fiber. One way of thinking about this is the following. So if you look at n upper one of YC, just forgetting about the fact that it's in a family, how can you think about it? Well, you can look at H2 with the integer coefficient of the fiber, okay, and then you just take the 1-1 classes inside this space. Now, as you barely see the point, the left-hand part here is topological, right? So it doesn't really depend on the point because all fibers are diffeomorphic here in the C infinity category. But this part is holomorphic. Okay, so this part here sees the variation of complex structure. Okay, and so in general, I mean, the fact that this part varies will give you the jumps in the Néron severity. This is why, in general, forming an upper one does not commute with a restriction profile. Okay, so this is all fairly standard. Now I need to tell you what are the two fundamental ingredients that go into our proof. So the first one is a result of Collar and Mori that they proved in the beginning of the 90s when the threefold MMP was being developed in full force. And so key input one. So this is Collar, Mori, Bosco Wisniewski. So as I said, in general, sort of these gadgets don't commute with restriction, right? But it turns out that if I look at MEY over C, so the sheaf of cones, the sheaf of molecones in family, and I just look at the K negative part, this thing is constant. So it's given by the negative part of the molecone of one fiber or any fiber times C. Okay, so if you wish negative K negative extreme arrays, the form. Okay, so even if I mean, if you dualize this observation here, you have that in general, not all one cycle classes on a fiber can be spread out to the whole family. However, in a smooth family, the K negative one can. Okay. And here, the fact that the family is smooth plays a crucial role. This theorem is completely false for singular varieties, even for mildly singular like KLT ones. The second key input this is due to Park building on work of Popper and Schnell, is that now if you have Y to be one, F, so this is a smooth vibration, then you can look at the push forward of the relative canonical to some positive power. Okay, so these are some vector bundle P1. And it turns out that this is the trivial vector bundle. So this is just a direct sum of copies of OP1 plurigenera of a general fiber times. Okay, so in particular, these are two pleasant consequences. The first one is if I take the relative canonical ring, or the direct sum of all the powers, this thing is nothing but the canonical ring of a general fiber, and then you just trivially extend it over all of P1. And the second pleasant consequence is that as graded rings, the canonical ring of a fiber, so KYC, is exactly the same as the section ring of the canonical device. So there is, again, there is no variation in the canonical models of the fibers. As rings, they are all the same. And not only that, but they also coincide with the absolute section ring of the relative canonical. I should say, so what goes into the proof of these theorems? So here, essentially, this is an application of the Conen contraction theorem played against the Lefschetz theorem. Instead, here, what they use is, well, when n is equal to 1, you see, this really boils down. When n is equal to 1, this piece is the lower piece in the Hodge filtration of the variation of Hodge structure in middle homology. Okay, but since we're over P1, that has to be trivial. When you take m greater than 1, you can, I mean, there is a standard trick called the cyclic covering trick that allows you to fall back into the n equal to 1 case. but I mean, it's way harder than what I just said, and you need to use a lot of mixed touch modules here. Okay. So now I can tell you how to prove one given these inputs. So, theorem one, let's recall, we had this situation, so we have F, this is a vibration onto a curve, right? It was not smooth, but we had, we can take an open set in C over which the vibration becomes smooth. And we know that this VHS is trivial. Okay, but so, you see, recall that I just told you that n upper one of a fiber, this was just the H2 intersect with the 1-1 classes. But now I'm asking, oh, sorry, maybe I should say, I should put a 0 here. I'm looking at the variation of our structure over the open set on which the vibration is. Now, if this is a trivial VHS, then it means that this guy is not moving. Okay, so where is it? These kind of issues when you have this jumping of neurons of the peak current, this doesn't occur. So since we have this variation of this trivial variation of our structure, as a freebie, we get that an upper one of x naught over c naught and lower one of x naught over c naught. These are both trivial local systems and commute with this change. Okay, this is nice. This simplifies our life a bit. And then what do? We look at the cone of curves, and more precisely, I look at the negative part. So you have this NE of x naught over c naught. I look at the k negative part, and so this guy lives inside N1 x naught over c naught with real coefficients. And because of P input number one, so this result of Collard, this shift is also trivial. Okay, so this is nothing but NE of a fiber times C naught. And so I'm just spreading all the extremal rays over the base. This is E input number one. Now, let me take sigma. This is trusting an extremal ray inside NE of XC negative. So this is integral extremal effective one cycle. We say that is minimal if minus k times sigma is smaller or equal than minus k times sigma prime for all sigma prime in R, again, sigma prime in R integral. Okay, so I'm taking an extreme array, and then I look at the smallest integral point on the array, which has, I mean, at the integral point on the array that has minimal intersection against minus k. Okay, so the smallest integral generator of the extreme array. Okay, now using random break, one can show that whenever you take sigma as above, so minimal, integral, effective, and blah blah blah. Whenever sigma, if you write sigma as the class of some effective integral one cycle, then this sigma is a rational curve. It's easy to see that it has to be, I mean, for sure, it has to be a reduced and irreducible one cycle by extremality and minimality. The hard part is to show, I mean, the harder part is to show that it's a rational curve, and this is exactly where bend and break comes into play. It shows that you can deform it and break it into two parts, and then repeat the argument until it has to become a rational curve. Okay. Now, because of the input number one, remember, this sigma lives in a fiber, but the negative part of the cone is just, I mean, it's just trivial over the base. So whenever I take this sigma, I can promote it to a flat family of one cycle, right? And each of these one cycle is itself a minimally integral extremal effective one cycle in each of the fibers. Promote sigma to, how did I write it? C over C naught inside X naught over C naught, such that when I take Z, I restrict to a fiber C, and then I take the numerical equivalence class, this belongs to the same extreme array and is minimal. For every C in the smooth dots. Okay, but now we are done. Why? Well, if I look at Z over C naught, every fiber by point 2 is a rational curve. So these are birational root surface, birational to a root surface. And so there's plenty of sections. So recapping, what I'm doing is I'm taking a k-negative curve in one fiber. I spread it out on the whole on the whole smooth locus C naught, and then by bend and break, I can say that since I took this class to be minimal, it's always represented by a rational curve. So this flat family of one cycles, if one possibly after normalization, but whatever, it has I mean, every fiber is a rational curve, and then it's very easy to show that in this case, this has to have section. If you want, there is this very powerful theorem of Greber and Weierstrass that tells you whenever you have a vibration over a curve and the general fiber is rationally connected, then there is always a section. But I mean, you can show it by hand here, you don't need to take this big hammer out. So I mean, these at least tells you where some sections are coming from when you have some negativity of the canonical divisor along the fibers. Any questions on this part?
I was gonna ask.
So, yeah, please. Sorry.
I was gonna ask about the Graver Harris study, but you already mentioned it. So.
Yeah, I don't know how to prove
I don't
clever.
know but sort of how it fits into this picture. Sort of.
Yeah, I mean, I'm sure. I mean, that, on the top of my head right now, yeah. But there has to, I mean, you don't, for sure you don't need to invoke Graver and restart to prove it's not like in this case, but sure it follows from that. But you see, it's a bit different. Of course, like if you have rationally connected varieties, you like those have like very negative K. Right. Here instead you don't require to be, I mean, you just want one.
Like, so even just for a Hertzberg surface, I mean, what's happening, like, that's another, we can just see that sort of by hand, so, a special case, so how does, I mean, that's all sort of trivial in this, in generality, or, I mean,
Well, I mean, in a Hilbert surface is literally a few, I mean, this is the Hilbert surface in this case, right?
Yeah.
Yes.
so, okay.
So I see that the class numerical class of ZC spread out. But yeah, could you please explain why the curve itself could spread out? Because it seems to me that to do this, we need to look at the relative Hilbert scheme of curves with class equal to ZC. And you're sort of claiming that this relative Hilbert scheme has a section. And is it yeah? Is it obvious that it has a section?
Well, I mean, I don't know in terms of the Hilbert scheme, but I mean.
Yeah, because the extremal, the curves representing the extremal class, curve class, in general is deforms also in the fiber. So you have a family of deformation of these curves. Then how can you how do you do so that you take one curve in the fiber and then you complete it into a flat family with connected fiber?
That follows from this. I mean, that follows from this theorem of Collard and Mori. I mean, this theorem is okay. Maybe it's not super clear the way I written it, but the point is that the negative part of this relative cone of curves is constant. I mean, it's a constant shift. And
yes, so I see that the class, you can spread up, but the curve itself, I don't. Yeah, maybe.
I mean,
Maybe I missed something.
Yes, there are two steps. First, you spread it out as an effective integral family of one cycles. That you can do because of this.
Yes.
Cycle. And then there is the bend and break part. An integral, yes, such that fiber-wise it's minimal. Because minimality only depends on this decomposition here.
Yes.
And then bend and break tells you that whenever you have a minimal integral effective curve class or one cycle class, then it has to be represented by a Riemann curve.
But the curve could be non-unique. Yeah, so it could be many curves which represent this.
I mean, yes, but I'm saying, I mean, it has to be represented by a flat family of one cycle classes.
Right? Yeah, in the fiber.
So and then I'm saying that I mean, fiber-wise, that flat family of one cycle classes has to be a rational curve. Sure, it could be non-unique. In fact, typically it's not, right? I mean, there are many curve classes in. I mean, there are many different in the same extreme array, or even in the same class. But no matter which one you pick, then fiber-wise it has to be a rational curve.
Okay, thank you. Maybe I'll ask after.
Okay.
Yeah, sorry.
But no, but I do agree that it's not unique. It's very much not unique. I'm just saying that when, however you represent it, it has to be by a rational curve. Okay. So now I can tell you about the group of two. So, okay, so what's the situation now? In the group of two, I mean, for two, what was the setup? We have X would be 1, F, so this is a vibration. And again, maybe it's not smooth, but we know that the relative canonical is Deutsch. And we want to produce a section of this thing. Okay, so now the first observation is that if I take Kx and then I add fiber, this thing is just the pullback of O minus 1. So in particular, it's not net, right? Now, I know that it doesn't exactly follow from what I said before, but the Cohen contraction theorem also holds for pairs. And if you're familiar with the NLP, this is not a surprise, but it sort of means that you can throw in an extra divisor with coefficient between 0 and 1, and such that the singularities of the divisors are not too bad. So since here I picked a general fiber, this guy is smooth and coefficient is 1, so Cohen contraction theorem also holds for Kx plus Xc replacing just Kx. Okay. So since it's not Neff, by the Cohen theorem and contraction, I can find R, an extreme array, which is Kx plus Xc negative. And this guy is still a rational curve. Okay, and I have an associated contraction. G equal to GR, say from X to B. Okay, and now we distinguish two cases. The first one is when the dimension of B is strictly smaller than the dimension of X. Okay, so this is you know about NLP, this is the modifiable space case. We're contracting down to something lower than. Okay, so in this case, we have the following picture here. X that goes down to B1 and G that goes to B. Okay. Okay, and now I'm gonna take the general fibers of G and F and intersect them and see what happens. Okay. So let's look at the canonical divisor of XC intersect XD. Okay, where XC and XC are general fibers of F and G respectively. Okay. First of all, I should say, observe that whatever G is contracting, whatever curve G is contracting, has to be horizontal with respect to the vibration. Why? Because it can't contract anything that is vertical, because on the fiber, this divisor, the canonical divisor is trivial. So whatever is contracting, it has to be transversal with respect to F. Okay, so it makes sense to intersect these two fibers. And then what we can say? Well, I mean, we can just do a junction. So you can say, well, this is K of XD restricted to the intersection with FC, but it's also K of XC restricted to the intersection with XD and FC. Okay, but nothing is happening now. But look, K of XC, I said that it was trivial, I mean, on a fiber. And if you further restrict it, it's still trivial. This is torsion. What about this one? This is anti-ample now. Because, I mean, this is a KX negative contraction. And so this, I mean, by definition, this has to be anti-ample. But so how can it be that it's both anti-ample and torsion? Well, the only possibility is if the intersection is dimension 0. Okay, so in other words, XB to P1 is finite. Okay. And now, if you look at what is KXB over P1, well, again, we can do a junction again. This is just KX over P1 restricted to XB. Just, I mean, I do a junction on a fiber. But this was trivial. And so when you restrict, remains trivial. So what does it mean? It means that XP is a dal over P1. But then it's an isomorphism because P1 is typical. So that's where the section is coming from. And notice in this case, you're proving really something way stronger. It's not that F has one section, it is uniruled by sections. Like every one of the fibers of G is a section for the map F. What about the other case? Well, you could have the dimension of V is equal to the dimension of X. So G is birational in this case. Okay, now, you know, again, if you know the MMP, you know that there are two cases here. One is a divisorial contraction and the other is a flipping contraction. For time reasons, let me just talk about the divisorial contraction, but the flip works more or less in the same way. Let's assume that it's a divisorial. So the picture is again, we have X, P1, and now we have G that goes to B. Now, again, whatever G is contracting is still horizontal with respect to the vibration. Okay. So in particular, if I now, the only difference is that now G is birational. So in particular, I can consider by precomposing in the inverse, I can consider a rational map phi from V to P1. Okay. And notice, I mean, this is really a rational map, meaning it has an indeterminacy. Why? Well, because you destroy the vibration structure by contracting something that was horizontal with respect to the vibration. So this is an honest rational map. And so you can show, I mean, by using standard MMP results, that the indeterminacy of phi has pure codimension 2. Okay, so from now on, for simplicity, let me localize at one of the generic points of this locus. So without loss of generality, I can assume that the dimension of X and the dimension of V is 2. I mean, it's not really without loss of generality. I lose properness, but it doesn't really matter. Okay, so now, what's the situation here? So you know that phi is given by a pencil of divisors inside V. What pencil? The strict transforms of two general fibers of F. Say G push forward of FC and G push forward of XC prime. So, and more, so what this is doing is resolving the indeterminacy of this pencil. Right? We have a rational map to P1, and then we are resolving the indeterminacy of the pencil, because here the map phi becomes a modus. So it's enough to show that the general member of this pencil is smooth at the indeterminacy. So, I mean, really, I want to say that at least if you localize the indeterminacy, the picture that you have is the usual one when you resolve an indeterminacy of a rational map, like the simplest kind. No, I mean, of course, if the general member is not smooth, then you can still resolve the indeterminacy, but the indeterminacy, I mean, does not produce a section. It produces a multi-section. Because whatever this divisor is passes with a multiplicity through the indeterminacy point. So really, what you want to show is the smoothness of this divisor. Okay. But this now follows at once from classification of singularities in the MMP, because we know that if x, xc is canonical, MMP preserves singularities. So I have that V with the push forward of xc. This is also canonical. And in dimension 2, these are completely classified. And so, and in particular, we know that this divisor here has to be smooth. And so this is where the section is coming from. Any questions? For the flipping contraction, the situation is sort of similar. You don't want to go directly to whatever you're contracting because this will have horrible singularities. And you need to take the flip and you need to run a more delicate analysis. But essentially, this is what the argument boils down. You want to argue that there is a rational map that is given by a pencil, you localize in dimension 2, in codimension 2, and then using classification of canonical singularities for surfaces, you want to argue that the general element of the pencil that gives the rational map is smooth. And so when you resolve the indeterminacy, it forces the appearance of a section. Okay. Is it okay if I go on until quarter past since I started later? Yes. Okay, so now I need to tell you sort of, given these two theorems, how do we recover Kilow's original statement? And note, I haven't used the key input number 2, which is the Park-Popa-Schnell theorem. Also, I don't remember if I wrote it, but in the key input number 2, the theorem of Park, Popa, and Schnell, they're assuming abundance. So that's why we also need to assume abundance. So if you're taking notes and I haven't written it down on the board, please add it because it's unknown without it.
So can I ask a naive question? So why does the extensional curve why cannot be a multi-section over P1?
Why can't the exceptional curve be a multi-section over P1?
Why it has to be a section, not the multi-section?
Because if it were, I mean, it's not. I mean, there can be rational curves that are multi-section. I'm not saying that every exceptional curve is a multi-section, but I'm saying that you can find one that is a section. And the reason is, the reason is all in this picture here. I mean, you are looking at this rational map, which is given by a pencil of strict transforms of general fibers here. Okay, so and these are surfaces without loss of generality. Okay, so I mean, you know that this resolves the indeterminacy, so you're doing some blow-ups. Okay, so I mean, what's the only chance for things to go wrong? Well, it's like you only have multi-sections of degree at least 2 if the general member of this pencil is singular at this point. But because MMP preserves singularities, this is not the case.
Okay. Uh-huh.
It's just that. It's just this simple.
Okay, thank you. Thank you.
Correct. Okay, so now proof of 3. So now we have f from x to p1, smooth vibration, and we want to show that there exists a section, right? Well, there are 2 cases. If kx is not fnet, then we conclude by theorem 1. Right? Because I mean, sure, kx is not fnet, so you have some negative curve in a fiber, and the variation of our structure over P1 is any variation of our structure over P1 is automatically trivial. So the other hypothesis of theorem 1 is satisfied. So that spits out a section for us. We need to worry about what if kx is fnet? What if it's net on all the fibers? The second case is yes, fnet. So what about? Okay, so now we use key input number 2. And what does key input number 2 give us? Give us the following picture. We have x over p1. First I'm gonna draw everything and then I'm gonna tell you what these guys are. Yeah, projection 2, f, and projection 1. So what is I? So actually, let me tell you first. I cross P1, this is nothing but the relative project over P1 of the relative canonical ring. And I, instead, is both the canonical model of a fiber or equivalently the ample model of the canonical divisor. And here I'm using both key input number 2 and abundance, because I'm assuming that the canonical divisor is net on the fibers, and abundance in particular tells me that it is semi-ample. So I mean, I have legitimate morphisms for netting all these varieties. Okay. And key input number 2, if you remember, it told us essentially 2 things. First, that the canonical models of the fiber are all isomorphic. And second is that they are all isomorphic to the ample model of the relative canonical of the vibration. So if you put all this information together, you get exactly this picture here. This is the relative canonical of x over P1. And if you go down to I, this is the absolute ample model of the relative canonical. Okay, very well. Now let me take a point here and form the fiber product. And let me look at G. So this is again a vibration, right, over P1. Y is smooth because I took a general enough point. And what can I say about the canonical divisor of Y over P1? And it's trivial, because this is a fiber of the ample model of the X over P1. So by theorem 2, G has a section. And so does F. This gives you an algebraic proof of Pilot's theorem. Of course, you're assuming the abundance conjecture, so it's far from a complete proof. But at least it's telling us, using only algebraic geometric methods, where are these sections coming from. They, roughly speaking, they come from extreme arrays of cones of curves, either of fibers or of the total space. Okay, so now I have still about 20 minutes. So I want to tell you a little bit what happens in characteristic P. Okay, so now let me switch gears. I'm going to be working in characteristic P, but I mean, my field will be algebraically closed always. So no worries about weird imperfect fields or related phenomena. So the first thing that I want to point out is that if you remember at the beginning, I told you that Pilot's theorem also holds when F has at most one singular fiber. And my first observation that I want to give you is this is completely false for one singular fiber. So, and the example is not hard to construct. So you can take E, an ordinary elliptic curve. So ordinary elliptic curve just means that you have P torsion points, and let's take one, okay? And then in characteristic P, there are these very weird covers of P1 called Artin-Schreier covers. So these are given by something like T goes into T to the D minus T. And these guys are branched over infinity only. So one way of remembering this thing is if you take the derivative of this guy, it's I mean it's -1 everywhere. So in particular, A1 is not simply connected in characteristic P, which is weird. But anyways, the point is that this is a Zimmer P quotient. And now you can do like the usual diagonal quotient construction. You take E cross P1 down to P1, the second projection, and then you act with CMOD P on P1 using the Artin-Schreier cover. You go down to P1, and you act with CMOD P on E cross P1, acting with the Artin-Schreier on the P1 factor, and translation by this P torsion point on the E factor. And you take the diagonal quotient, and you get some X, P1. And now, I mean, it's pretty easy to convince yourself that this guy here will have only one singular fiber, one singular multiple fiber over infinity. And so in particular, you cannot have a section. You cannot have section for morphism that have multiple fibers. All good? Okay, I mean, this is, this takes care of, it answers negatively the question about Pilot's theorem in the case of one singular fiber. But what about for smooth morphism? Well, it turns out that Also for smooth morphisms, the theorem is false. But showing, constructing an example is considerably more complicated. But I want to tell you sort of, again, where are these things coming from? So, okay, foliation. So if x over k is a smooth variety, a foliation currently F inside the tangent bundle is a saturated shift such that the following conditions are satisfied. I want it to be involuted, so closed under V brackets. This is the usual, the usual local integrability condition. And in characteristic P, you also want to ask that it's closed under P power. So if you have a derivation, you can iterate it P times. In characteristic P, it turns out that this is also a derivation, and you want to say that the foliation is closed. I mean, this subsheet is closed under this operation. Okay. Now, one nice thing, one of the few nice things about characteristic P geometry is that given a foliation on a variety, you can always construct the quotient by the foliation. Okay, and how does one do it? Well, so in characteristic P, you always have a finite morphism called the Frobenius. So the Frobenius is just an identity at the level of topological spaces. It's an homeomorphism and sends every function to its p power at the level of sheets of regular function. Okay, so the way that one defines the quotient of x by the foliation f is the following. So it's something that factors this Frobenius morphism. And it's simply defined by taking spec over x, this x, of Ox of f, where Oxf, this is just the subsheaf of functions in Ox such that they are killed by all the derivation inside the foliation. So let me give you, let me give you an example of like, what is this thing doing? So, for example, I can take x equal to a2 and take the foliation given by dx. Okay, so then I can take a2 and go to a2 more f. And what is this? Well, at the level of regular function, this is just k of xy. And what are the functions that are killed by the foliation? Well, for sure, you have y, because doesn't depend on x. But then you have x to the d. You're doing Frobenius on one factor and leaving the other one untouched. And of course, it's pretty clear that it fits in a diagram like so. To complete, you just take the p root of the y. Okay. Cool. So So now the key to constructing the counterexample for smooth morphism are these so-called Moreva-Eve entities. So here is how one constructs it. So let's take E. Now this is a super singular elliptic curve. So super singular elliptic curves, this means that there are no torsion points. I mean, no non-trivial torsion points. Elliptic curves in characteristic P, they come in two flavors. The ordinary ones, which are the majority in a certain sense, which have P torsion equal to C mod P, and the super singular ones that are in some sense special, that have no non-trivial torsion point. However, one should be careful because, I mean this as a group. As a group scheme, this guy is very much non-trivial. It's a non-trivial extension of alpha P by itself. But I don't want to get into that much. Anyway, so the point is that once you have this gadget, there is this you can do the following construction. Let's take A to be just the product of P times C. And let me call P be the projectification of the Lie algebra of A. Okay, now on A times P1, P, I guess, we have F, a tautological foliation. So what is this foliation? Well, if I fix a point in P, what I'm doing is I'm selecting a tangent vector at the origin inside A. Okay. And this is the one that gives me the foliation. Okay. So as I vary the point on P, I'm selecting a different tangent vector in the Lie algebra. So this gives me the tautological foliation on this one. And then I can just force the quotient. And in the same sense that I just described. Now, this foliation respects the fibers, but made essentially by construction. So I'm getting this quotient. This quotient variety also admits a map to P1, and this is called the Moreva effect. So its most important feature, besides the way that it's constructed, is that this is a non-isotrivial. It's a non-isotrivial, non-trivial, sorry, abelian scheme over P1. So this is something that absolutely has no analog in characteristic zero. You cannot have a non-trivial abelian scheme over P1. Every abelian scheme over P1 has to be, but this is not. This is very much non-trivial. Roughly speaking, what's happening is that the geometry of the fibers is controlled by the way that this infinitesimal group scheme is embedded inside A. And since you are varying it, that's where the non-triviality of the quotient family comes from. To make this precise, you need to use something called Theodor-Ney modules, which I'm also not very familiar with. But anyways. Okay, but this is an abelian scheme over P1. And so in particular, if you remember what we said about non-algebraic counterexample to Birov's theorem, they arose as E torso for an elliptic curve. So now what we did is we compute the FPPF homology in degree 1 of this group scheme, and we showed this is non-zero. So this is essentially a very long computation in group cohomology, sorry, in FPPF cohomology, which uses a bunch of results that are hidden in Reynolds thesis. Anyway, you do this computation and you show that you have non-trivial M torsors over P1 for M de Moreau-Bagui family. And so in particular, these guys will give you an example of a smooth morphism over P1 without any section. Okay, so I have 5 minutes, so let me just conclude by telling you what we can prove in positive characteristics. So in what follows, I will always assume cone and contraction theorem. So cone theorem, sorry, for smooth varieties. So the cone theorem is, if you're familiar with the proof, is not you're really not. I mean, you're not really assuming it. The cone theorem is proven by reduction to characteristic P. This is not really a big assumption. The contraction part, however, is. We don't know whether we can always contract extreme arrays in higher dimension, but in dimension up to 3 is okay. So assuming this, here is what we can prove. So theorem 1P, I guess. So let me assume that we have X over C, F, so a vibration again. And I'm not asking it to be smooth, but I'm asking that there exists a big open on which this thing is smooth. No, now this, I mean, you need to ask this because, I mean, in characteristic P, Sard's theorem fails. So, I mean, you can have vibrations on which every fiber is singular. So I'm asking that at least generically the vibration is smooth. And then such that A of F naught is not F F or F naught F. So same assumption as before. And then instead of asking, we have a trivial variation of Hodge structure in degree 2. We ask the same for crystalline cohomology. Up to lower star of X naught or K, the trivial F isocrystals. So crystalline cohomology is essentially, I mean, it's a wide cohomology theory that plays the role, sort of mimics the rank cohomology in characteristic 0. And in this case, it's playing the same role. Linear section. The proof is exactly the same. The only difference is that I mean one very much non-trivial input that goes into the proof is a variational version of what's called Tate conjecture for crystalline cohomology that has been proven by Morrow a few years ago. That's a very, I mean, that's an extremely non-trivial theorem that thankfully somebody else has proven for us. But it roughly says that if you want to lift a cycle class in degree 2 from a fiber to the total space as an algebraic cycle, it's enough to do it at the crystalline level. And so this assumption exactly triggers that hypothesis and allows it. And the second theorem, which is the characteristic P version of theorem 2 is that now suppose we have f thanks to p1, again a vibration, generically smooth. And then and such that again kx over p1 is trivial, and we need to ask a bunch of other hypotheses. Oh, sorry. Sorry. Then, so here we don't need other hypothesis. Then F as a section. Here the proof again is the same as before, because we assume, I mean, if you remember before, we just assume Cohen contraction theorem, and we didn't need much else to conclude. Where we need the extra hypothesis in theorem 3P, which is the characteristic P version of Pilow's theorem. So suppose F thanks to P1, a vibration which is smooth, and either Kx is not Fnet, or if it is Fnet, we want that Xc, the fibers, is a good minimal model. So we want Kxc to be semi-ample, not just net. Not only that, but we want it to be canonically fiber. So this hypothesis means that semi-ample, okay, let me write. Kxc induces the Hitachi vibration. So being a good minimal model means that for big M, for a big multiple of this guy will be base point free and induces a vibration. Being canonically fiber means that M equal to 1 suffices. So really the canonical class on the node induces the vibration. It's sort of like an analogous hypothesis to the canonically polarized variety, canonically embedded variety. Maybe in this case, the canonical is not ample, so instead of giving an embedding, it just gives a vibration. And then we want that when I look at the middle dimensional homology, crystalline homology of a fiber, this is torsion free. And this is to avoid this kind of Moré-Bailly pathologies that we discussed before. Then, there exists a section. So this is how Pilow's theorem generalizes in characteristic thing. I mean, it's not sharp, of course, because I mean we're asking a lot here. Yeah, this is what we can do at the moment. And I should say, I mean, if you remember, one of the key inputs in proving 3 was that you don't have non-trivial variations of our structure on V1. It was proven by Hélène Hainaut that the same is true for F isocrystals, so this kind of gadgets coming from crystalline homology. It's all that when you are on a simply connected basis, also they also have to be treated. So in this case, thank you for your attention.
Thank you, Jacopo. Are there any quick questions?
So in your theorem 2, can you say anything about the sort of the structure of the vibration? And if X had a symmetry 2, for example,
Yeah,
all fibers going to be isomorphic. I mean, if it's a threefold, could you have non-isomorphic?
here I mean in this theorem too.
No, in the other theorem too. So when we do have a section, so actually the P1 has a section with the relative non-trivial.
Yeah, I mean, that's actually, yeah, okay. So, I mean, I can't, I mean, I can say what I expect. So I think that, I mean, this theorem is I mean, you do have a section here, but I'm not so sure whether this condition automatically implies that all the fibers are isomorphic. Because, so I mean, what we can prove, or I should say what Ben can prove, is that if you have a smooth vibration over P1 of good minimal models, then they are all isomorphic. But this is not exactly the situation we are in, right? Because I mean, I'm not asking the vibration to be smooth here. However, if you're familiar with the canonical bundle formula, I mean, this is a K-trivial vibration. So in general, for a K-trivial vibration, you know that you can write Kx as the full vector of K of whatever is downstairs. So P1 in this case, plus some moduli part that comes from the variation of Hodge structure, plus some boundary part that measures the singularity of the singular fibers. Now, if I ask that thing to be trivial, means that these two guys are not there. So, I mean, so there is no variation of our structure in the middle in middle degree, and this doesn't mean that the vibration is smooth, but it means that it's at least semi-stable. So at least all the fibers have, I mean, log canonical threshold equal to 1. So this is not exactly saying that it's smooth, but it's placing like a very big constraint on the type of singularities that you can have. Now, as of now, I don't know if I mean, I don't know if this thing implies that all the fibers are isomorphic.
Okay, I was just thinking, yeah, look, if X had dimension 2, and I have a section from P1, I would want it to be split.
Yeah. No, I agree. This is still in progress. The result is correct, but then like.
And then another sort of question is, so how do we construct sort of I guess smooth vibrations over P1, say even when X has dimension 2, that we sort of don't already know that they have a section?
It's not easy. It's not easy. Yes, I mean, so Ben, for example, Ben has a paper, a recent one, in which he constructs non-isotrivial families of Fano varieties. But my impression is that if you want, I mean, first of all, it's very much not obvious. I mean, it's not an easy construction. It seems to me that if you want the fibers to have non-negative Kodara dimension, this is extremely hard. You need to have maybe rationally connected or uni-root fibers, and then some like positive dimensional isomorphism groups, and then you can start playing these twisting games over P1. Yeah, no, it's I mean, in fact, the whole theorem is telling that it's very rare to have a vibration over P1. That is, I mean, in characteristic pieces, yeah, but
Yeah, thank you. So if there are other questions, then maybe let's ask Niccolo after the talk, because we'll have another talk in 7 minutes. Yeah, so thank you, Niccolo.
thank you.